In today's notes, we're going to do a quick review on how to tell if a function is even or odd, and then we're going to add in how to prove algebraically whether a function is even and odd. So I would take notes in your notebook, have your graphing calculator ready to go, and pause the video whenever you need to. So we're going to start with even functions. So we can tell graphically that a function is even if it has y-axis symmetry. So this is an example of an even function. Take a minute to type it into your graphing calculator right now. So when you put it in your graphing calculator, you can see it's just a flipped parabola that's been moved up 4, or maybe you would even know that just from using your transformations. So just making a quick sketch of this. Function looks like a flipped parabola that's just been shifted up 4. So we do have that y-axis symmetry, which is how we know that it's even using the graph. To tell whether it's even using the equation, what we have to do is prove that when you plug in the opposite of x, you get the same thing as when you plug in just regular x, and you have to prove that for all possible x. So we start by plugging negative x into the function, and just make sure to always use parentheses. So this one's a little bit weird because we have a negative that's a part of the equation, and we have a negative that's a part of the x we're plugging in. So just make sure to use parentheses to be clear. And then we work on simplifying. According to order of operations, we should apply the exponent before we do the negative out front, because that's like multiplication. So negative x squared is negative x times negative x, so that would just give us a positive x squared. And then we have to put that negative back out front, like that, and then plus 4. Now, if we compare this to the original function, we can see that it's the exact same expression. So when we plugged in negative x, we got the exact same thing as if we would have plugged in x. So that's another way that we know that it's even. The last thing that we're going to do with even functions is talk about which trig functions are even. Obviously, there's a whole bunch of trig functions. We're just going to stick with the basic 3, though, sine, cosine, and tangent. So the only one that is even is just cosine of x. And that's because it has that y-axis symmetry. That also means that if I took some x on the graph, like let's say this one, and I compared its output with the opposite of x, I would get the same value. So what that means is if I'm trying to simplify cosine of negative x, that's just going to get me the same thing as cosine of x. And the reason that is because it's even. When I plug in the opposite of x, I get the same output as when I plug in just regular x. All right, take a minute to look over your even functions, and when you're ready, we're going to move on to odd functions. Pause if you need to. All right, odd functions, they have what's called origin symmetry. That means we can rotate them 180 degrees around the origin, and they're going to look exactly the same. So this is an example of an odd function. Take a minute right now to type that into your graphing calculator to see what the graph looks like. Next thing I would do is make a quick little sketch of that in your notes. All right, so we can tell that this function has origin symmetry because if we spin this thing 180 degrees around the origin, it's still going to look exactly the same. So that's one way that we know that it's odd. The next thing we're going to practice doing is determining how a function is odd by using its equation. So what that means is if we plug the opposite of x into the equation, we should get the opposite output. So if I'm testing it algebraically, I'm going to start by plugging negative x in for each x, and then simplify. Once again, make sure to use parentheses. And then we're going to make sure we simplify using order of operations as well. So negative x to the third, negative x times negative x times negative x, overall will end up being negative. And then when I subtract a negative, that's the same thing as adding a positive. And when we compare that to the original function, we can see that each term is opposite. The x to the third changed to negative x to the third, and the negative x changed to positive x. So since each term is opposite, we can say overall it's the opposite of f of x, and it's going to be odd. I put the little note up there, if function has multiple terms, all of the terms must be opposite. So it can't just be some of them, it's kind of an all or nothing deal. All right, then the last thing we're going to do with odd functions is talk about which trig functions are odd. So out of the main three, actually the other two are odd. So the first one that we have here is sine of x. So the reason that sine of x is odd is because, one, it has origin symmetry, and two, if I try to plug in an x value, let's say I pick this x value, if I compare its output to if I do the opposite of x, so the same distance just in the opposite direction, they're going to be opposites of each other. So this one up here is positive, and this one down here is negative. So what that means for simplifying is if I plug a negative x into a sine function, I'm going to get the opposite thing as if I plugged x into the sine function. So when we're simplifying, that's how we'd simplify. And then kind of same thing down below here with tangent. Tangent's odd because it has origin symmetry, or if I picked any x value and looked at its opposite, I would get the opposite output. So if I'm going to try to simplify plugging negative x into a tangent function, I'm going to get the opposite as when I plugged x into the tangent function. All right, take a look over the odd functions. If you have any questions, go back and rewatch the video or ask a question. All right, last thing to take a look at is what if a function is neither. So basically what happens is when you graph this thing, you're going to have neither y-axis symmetry nor origin symmetry, or if you plug negative x into the function, you don't get the exact same thing or the exact opposite. So this first function right here is neither. If you plug it into your graphing calculator, x to the third minus fourth, it's basically a cubic that's been shifted down 4. So it looks something like that. So we don't have y-axis or origin symmetry for this one. And if I try to plug negative x into the function for this one, start simplifying, this will be negative. What happens is my x to the third changed signs, but my minus 4 stayed the same. So overall the function didn't stay the same, and overall the function didn't become opposite, so that's one way we know that it's neither. And then there's just one last example of neither. So same thing, take a second just to put that in your graphing calculator. When I graph this, I get a parabola. But since my vertex isn't somewhere along the y-axis, it doesn't end up having y-axis symmetry. It also doesn't have origin symmetry, because if we turn this 180 degrees around the origin, it would end up upside down and wouldn't look the same at all. And if we check algebraically, plug in a negative x for the place of each x, what ends up happening, negative x squared is going to become positive, and then a negative 2 times a negative x is going to become positive 2x as well. So just like the last time, I have a little bit of each. The x squared stayed the same, the negative 2x became positive. So overall, it didn't stay the same, and overall, it didn't become opposite. So that's how we know that it's neither.